EES, which is pronounced EASE, is an acronym for Engineering Equation Solver. EASE provides property information for many different substances. The calling format for the property functions depends on the nature of the substance and the type of property that is desired. The format of all the property functions can be examined most conveniently by selecting Function Information from the Options menu in order to access the Function Information dialog, which is shown here. And then you select Thermophysical Properties in this radio button, and what you'll see here is the palette that shows the 6 different categories of built-in property data available in EASE. There's additional property functions also available up here in the library routines and the external routines. Information on each of these alternative sources of fluid property data is provided in the videos in this section. This video discusses specifically the real fluid property data. In EASE, the term real fluid refers to fluid property models that make no fundamental simplifications. So the fluids are represented with compressible fluid models that can describe the substance all the way through its compressed liquid to its two-phase to its superheated and supercritical states. You can see some examples of real pure fluids here, so acetone, argon, and things like that. Real fluid mixtures are also included in this category, and this refers to azeotropic or zeotropic mixtures of fluids with a fixed composition. So for example, R507A is a 50-50 mixture of R125 and R143A. There are many thermodynamic and transport properties, but they're all related by the phase rule. So the phase rule dictates that the state of a pure fluid or of a mixture with a fixed composition in a single phase condition is fixed by specifying the values of 2 mass-independent properties, so 2 intensive or specific properties. The calling protocol for the typical property function then is shown here. So function name refers to the name of the property function that's being called, and the name of the function corresponds to the property that is being returned. So for example, enthalpy is a function that returns specific enthalpy. Volume is a function that returns specific volume, and so on. The first argument, fluid $, is a string that specifies the name of the fluid that's being considered. Then you need 2 properties to fix the state. So the second and third arguments indicate both which 2 properties are being specified as well as what the values of those properties are. So property 1 equals is an indicator that identifies what the first property is. And then value 1 is the value of that property. And then property 2 and value 2 are the indicator and the value of the second property that's required to fix the state. So for example, if property 1 equal is T equals, then that says that temperature is specified. H would indicate specific enthalpy is being specified, and so on. So we'll talk in a little bit about a list of all the legal indicators that can be used with real fluids. Note that the values of the properties, so value 1 and value 2 that you provide here, must be in the same units that are specified by the unit system, and also that the function itself is going to return the value of the property in the unit specified by the unit system. So as a real simple example, let's determine the specific volume of the refrigerant R134A at a temperature of 350 Kelvin and a pressure of 250 kilopascal. So first I'll set the unit system, and I'm going to use the $unit system directive, and then I'm going to call the function volume to get specific volume. I'll tell it with the first argument that I want R134A, and then I'm specifying the state with temperature, so T equals, and then the value is 350 Kelvin, Kelvin being the same temperature I used in the unit system. And P equals says I'm going to also tell you the pressure, and 250,000 is the value in Pascal, and again Pascal being consistent with this unit system directive. And if I solve, I will get that V is 0.1108, and the units of V must be meters cubed per kilogram because that's the unit of specific volume consistent with the units that I've set. So you're going to note here that EASE is going to check to ensure that the units of the input temperature is Kelvin, the units of the input pressure is Pascal, and also EASE is going to check that the units of the variable B has been set to meters cubed per kilogram. And if any of these conditions are not met, then EASE will issue a warning whenever it checks units. The left-hand box in the function information dialog provides a complete list of the properties that are available. So if you select function information, you'll get more information about whatever property it is that's being returned. This is a partial list of some of the most commonly used thermodynamic and transport property functions in ease that are applicable to real fluids. These properties are probably pretty familiar to most mechanical engineers. The possible units of the value that is returned are shown over here in the SI and English unit systems, and these units are consistent with having set up the unit system to be on a mass basis. If you have instead selected on a molar basis, then you would just replace kilograms with kmols and pounds with pound moles. There's a number of less familiar properties also available in ease. These are listed here, and they're called in the same way. They're just maybe less familiar to most engineers. And then there's other properties that return more general characteristics of the fluid. So maybe it's molecular weight, or properties that are specific to the fluids in the vapor dome. So things like saturation pressure or critical temperature. And we'll cover some of these more unique properties in a subsequent video. All the property functions require a string that contains the name of the fluid as the first argument in the function call. A list of the fluids that are implemented in your version of ease is shown here in the right-hand box of the function information dialog. The names of the built-in real fluids that are available at this time are provided in this table, but you should note that fluids are constantly being added to ease, and therefore this list continues to grow. Again, this list consists of mostly pure fluids, but also some mixtures of fixed composition, and in particular the R400 series are zeotropic mixtures, and these are mixtures that typically exhibit some kind of temperature glide within the vapor dome. So the temperature of saturated liquid will be different than the temperature of saturated vapor at a specific pressure. And then the R500 series are typically azeotropic mixtures, and these behave essentially like a pure fluid. You can select fluid information in the function information dialog to get more information about the source of the property information that's being used for whatever fluid that you've picked. So this is going to include references that will tell you exactly the source of the data or the equation that are being used by the property function. The thermodynamic and transport functions for real fluids that we've discussed in this video again require two properties be set in order to fix the state. Ease is flexible with regard to which two properties you use to fix the state and also what order you provide them in, and that's why you need an indicator to specify which properties you're providing. The indicator is a single case-insensitive letter that's followed by an equal sign. The property indicators that are recognized in function arguments and their meaning are listed here. All of the property functions provide an example of the proper function call in the example box that appears just above the paste and done buttons in the function information dialog. So for example, here I've selected the property enthalpy in the fluid ammonia, and then down here in the box labeled independent properties, the user can select the two properties that are going to be used to fix the state. So here I'll fix the state with specific volume and temperature. In many cases, each independent property corresponds to an entry in an array of properties, where each index in the array corresponds to a state in the cycle. And therefore, if you want, you can fill in this edit box over here to the right of the example box with the information about the state. So if I put in, for example, in square brackets 1, that's going to be appended to each of the independent variables in the example call here. The text provided in the example box at the bottom of the dialog then adjusts to conform to all of my selections. And if I select paste, then the resulting property call will be pasted right into the equations window, saving me the time of typing this myself. So this is one of a series of tutorials that's meant to describe the operation of the ease software. If you want to get more information about ease, obtain the software, or access more of these tutorials, please go to the website fchart.com. These tutorials are excerpted from the book Mastering Ease, which can also be obtained from the FChart website.